Hi everyone, my name is Shen Qiu. I'm from Alibaba. So we have another speaker named Min Ning. He will also talk about some part in the slide. So I just talk about the first part of the slides. So in this slide, we mainly cover some topics why we choose SPDK in our production environment, especially provide a high-performance storage service in Alibaba real deployment. And also we will cover some of the problems we have made when we met when we use SPDK in our environment. And we will talk about some solutions we have done to resolve these problems, and also we hope we can get some feedbacks from the community and all the other peoples. Also welcome for your comments, what we have done. And in the last, we've talked about some future plan with the SPDK community. So here's the outline. So basically, why we choose SPDK. So performance is first consideration when we think about SPDK. So as everyone knows, as a storage device become more and more faster and provide low latency, high bandwidth performance to the applications. So how to make the storage I/O stack more efficient and also more lightweighted is critical to explore these high performance devices, the Lambers. So that's the reason we choose SPDK, since SPDK provide a very efficient implementation in the user space and provide us very low latency I/O stack, and also very flexible, extendable software stacks for us to customize for our applications requirement. So basically the second consideration, how to extend and how to customize. So SPDK, since it's in the user space, so it's very provide us a very flexible space to extend the I/O stack for our specific usage model. For example, if we consider about the quality of service, since we have different applications and different service providing on the up layers, so this application and the service may require different performance. Some are maybe very I/O intensive. They require large bandwidth, but they're not critical task, and some others may be very latency sensitive. So for these different requirements, maybe we want to add some specific I/O scheduler or some QoS design on top of this I/O stack. So in SPDK in user space, it's more easier to extend this service. So the last part, basically, also SPDK provide a very strong community support. So there are a lot of experts there. So when we have problems, so it's very convenient to basically get some feedbacks or comments from the community. So these are the three basic considerations why we choose SPDK. So in this slide, basically basically we cover some problems we have met when we adopt SPDK to deploy our storage service provide to our applications. One critical problem is, I think, as a previous speaker from the Oracle, they also made similar problems. Basically, the limited NVMe pairs from the devices side. Because in our environment, we need to deploy a large number of applications on a single server and also on even a single device. And basically, we provide container also other running environments, so the application can be switched from machine to machine, device to device, and so we cannot basically allocate static fixed number of MMQ pairs for each process. First, there won't be that large number of MMQ pairs we can allocate. So for example, typical NVM device maybe only provides 32 Q pairs. So that gives us the limitation of running only 32 application instances on the same device. And the other, so if we want to make this application can be shareable on the same device, so one possible way is maybe share the NVMQ pair between applications. But this also gives another problem, that is the lock contention. So as SPDK is designed to be lock-free, so one application basically when you submit I/O, you don't need to lock the queue and you don't need to contend with other threads or running processes. So more important is so since you are sharing the critical data structures among processes, for example, if one process when it submit I/O, it lock the queue, and then this process crash, and this queue cannot be accessed by other process since the lock may be also a shared memory implementations. So we look at whether there are some existing approach we can utilize from the SPDK part. So SPDK architecture provide another good thing called vhost architecture. So this architecture basically provide a virtualized layer above the physical devices. So applications can just access I/O devices, and then the vhost handling the actual physical device resources such as MMQ pairs and other resources. This seems good since applications they can just create the virtual queue, which is implemented as just a ring buffer at the virtual device side, and vhost side just manage the physical queue pair. Maybe we can just allocate one queue pair per virtual device, or we can have multiple queue pairs for multiple virtual bdev devices. But since the current implementations from the vhost-scsi targets, it does not allow multiple connections to the same target, which means if we want to have one vhost target which is shared by multiple applications, this cannot be used using the existing implementations. Moreover, when the vhost crash, so then the vhost has to restart, and then the I/O device has to reconnect to the vhost. Also, this requires a restart of the application side, which is not acceptable in our usage models. In order to overcome these issues, we have done several patches to make the vhost to be usable in our real production environment. So the first patch we have done is to support the multi-process access to the same vhost target. In this way, we don't have the queue pair limit, and also we can have multiple process to access the same target, share the same target. The second one, basically, we add some auto recovery mechanism in the SCSI initiator side. So once the vhost crash, we can detect vhost crash, and when the vhost restarted, then we can re-establish the connection with the vhost and basically rebuild the word IO size queue and resend the pending IO. So all these are transparent to the applications. So for the first patch, we basically made these changes to the vhost target code. So we changed basically the vdev from a single pointer device to just an array of the vdev devices. So each target can manage multiple connections instead of just one single connections. And then the vhost side worker, the IO worker and the admin worker, when they handle the IO and when they pull in the admin IO and the request IO, they will loop through the connected devices, collected VDV devices, and then basically handle them. When there are any word IO device removed from the vhost target, then we will monitor that event and basically remove that disconnected device from the vhost side. And for the second patch, basically, we built some auto recovery mechanism at the word IO side. So this chart just describes the logic of the flow. So when the polling thread at the word IO initiator side, when they try to pull the completion event, they also check whether there are any IO timeout happens and pending IOs. If there are IO timeout we found, and then we check the vhost libraries. So we send some heartbeat to the vhost monitor socket to the vhost socket, and then the vhost process basically is protected by the systemd and service. So we register as a daemon. So if vhost crash, and the systemd will restart the vhost process. So once the vhost process is restarted and initialized, then the initiator side will find that, okay, this vhost is live now, so we can reconnect to this vhost. And then when the reconnection is down, then we will resend all the pending IO, and all these basically are transparent to the applications. So what happened at the word IO initiator and the bdev code. So I think so Min can cover the remain of the slides.
Okay, so yeah, actually I feel tired, I feel sleepy, so I guess you guys are the same as me. So just wake up, I only have 2 slides to talk actually. So before I start, first I want to thank Ben. Actually, at the very beginning of this project, we have had a lot of discussion with Ben, and he suggested this vhost.io and vhost architecture, and actually it works pretty well in our production system. So yeah. So you know, we run our product on Alibaba Cloud, so we care about the instance start time a lot. So our target is actually we need to schedule an instance, start the application in less than 0.1 second, 100 milliseconds. Now we get like 0.3 seconds. So here's an example. For example, in my test system, I use a 10 gig huge page. Every application uses 250 meg huge pages. So you see the original means the current code, the original code, the upstream code, it will scan, sort all 3 huge pages. Even the application only uses like 256 megabytes huge pages, but it will still scan and sort all the free huge pages. So it takes a long time. For this example, it takes about 7.5 seconds. Then we made two changes. One is to the DBDK, another is to the vhost-scsi. So I listed here 1 and 2 here. Mass scan, we add a new parameter, mass scan mem to DBDK. So with this parameter, it means we only scan so many huge pages as specified by the parameters. With this change, the start time, application start time dropped from 7.5 seconds to 1.8 seconds. The other change is to the vhost-scsi. So by default, now when the vhost-io initiator connect to the vhost target, it will scan by default. There's a macro, it's a hardcode thing, so 64. It will try to scan 64 targets. This also took some time, more than 1 second. So we add a new parameter to the vhost-scsi configuration file. I call it a SCSI target. For example, next example, it means the vhost-io SCSI initiator will only scan target 0. Because in our application, one initiator will only connect to one vhost target. So this is good for us. And here's the patch. So now we get a 0.3 second application boot time, but now our target is 0.1. Actually, last week I also heard from Ben, the DBDK now has a new feature with the latest DBD code. It will not pre-allocate all the huge pages. It will allocate the memory you needed on the fly. So maybe we will look at it and we will try to port it back to our system. I think it will save even, maybe we can get a 0.1 second target later. Yeah. Okay, another thing is we modify the Reactor thread on the initiator side. It's kind of hard to change this on a server vhost side. So the first thing we did is at the initiator side. So we will deploy tens of applications on one single machine. For example, probably 50 or 60 instances. So we cannot use, on our application, we cannot use the busy polling mode of the Reactor thread. So we borrow the code from SPDK, and we did some change. We implement our own sleepable Reactor thread in our application side. So this is the flow. It's kind of very straightforward, actually. So the application submit a request, and then we have some kind of a counter. We call it NR request to record how many requests on the fly now. So then we'll go to the main Reactor thread. One more thing is we will first check if the Reactor is asleep. If it's asleep, then we will wake up it, use the pthread condition variable. Then we go to the Reactor thread main loop, then check if the NR request is 0, it means we have handled all the requests. So now you can go to sleep with the pthread condition wait. If not, then the thread is the main loop will continue to handle other requests. So, by the way, in the DBDK, there's a parameter called max delay, but it doesn't work for us because once the initiator connected, then on the vhost side, there is always at least one active poller. So even you specify max delay, it will still keep do the polling things. So we'll always keep the core busy, 100% busy. So that's why we cannot even use the max delay parameter. Yes. So here I didn't send the patch out because as I said, I borrow code from SPDK line. We add the code in our own application. So later, maybe I can try to integrate this change back to SPDK. I mean, if the community thinks it's a good thing, we can try to do that. Oh, sorry. Yeah. So yeah, here's the future plan. We like to contribute to the community. So that's why we have sent the 4 patches out on the mail list. Because the patches were based on the old SPDK 17.10. So now we have not made a GitHub review. We have to port the patches to the latest master branch. Then we will make an official GitHub review later. We like to contribute, so the community, it will also help us. The community can help the review. Probably somebody can also help the test. Then we can do better in our own production system. We can make our code more robust, more stable. Yeah, yeah. So that's it. Thank you. Any question?
So when you put your reactor to sleep, with the conditioning variable, how do you determine when to wake that up? What's the signal mechanism to wake up the reactor again?
Sorry, let me go to here. Oh, sorry. Oh, sorry. Okay. Sorry, could you repeat the question?
I was saying your conditioning variable reactor, when you put the reactor to sleep, what's the mechanism to wake that up in an efficient manner?
Oh, so in the main loop, if the counter drops to 0, we will means now there's no pending request. All requests are already handled. So now we can go to sleep.
Right, but then how does it work? What wakes that reactor up again?
Sorry?
Then how does that thread get woken up again?
Oh, yeah, this part, because that's why I said it's easier to do these things in initiator side, because the application knows it's the application submit the request.
Right, the application sends it, on the initiator side, the application sends a new
so
request, and that wakes it up. Okay.
Yeah, absolutely, yeah. So it's harder to do these things in vhost target side.
On the target, right.
Yeah, because vhost target, he doesn't know when the IO request will come. So he already need to do the polling.
Okay, so you only did it with the initiator. Okay.
Yeah.
Yeah. You were using vhost-scsi. Why aren't you using vhost NVMe? Because I noticed you were using NVMe devices in your implementation.
So your question is why we don't use the vhost NVMe? Two things actually. Last year when we started the project, there's no vhost NVMe yet. Another thing is there's no virtual NVMe library on the initiator side even now. So, and the third thing is I think probably the performance, maybe the better things for us is the virtual BLK. The performance maybe will be better than the virtual SCSI. But last year we thought that the virtual SCSI probably is more stable than. Oh, one more thing is that in the beginning of this project, there's no virtual BLK either. So actually, we have no choice.
You had no choice.
The best choice is virtual SCSI. Yeah.
Any other questions? All right, thank you guys. Good stuff.
Thank you.